introduction to R. I know that some of you might not be familiar with R, so it might be a good introduction. It is a kind of a gentle introduction to R and coding in general. Um, and for you guys, for everybody, for people here who already have like a kind of a background in R, it might just be a little bit of an a refresher. And so that's why I think most of you have had some sort of exposure to R in at 500, so that some of that stuff might be a little bit of review. But if we get to it, we get to it. And again, I'll help you through the coding part of it. For the most part, that'll be left up to the homeworks. But apart from that, yeah, we can kind of do a little bit of coding here and there. Um, Before I start, are there any questions about what we talked about last week? You have 1 week left to submit a project proposal if you're going to do a project, if you're going to do a course project that's going to be more than one person. It's 2 weeks from our first class. And I think that's about it. Unless anybody else has any questions. No homework due today. There will be no homework for next week. Just the most important thing is to start thinking about your course project. In my experience, the people that spend more time thinking about their course project and coming up with a good idea at the beginning of the semester aren't rushing around at the end of the semester trying to put something together, and it shows, right? And so, being that there's no homework yet, being that I haven't given any homework yet, spend some time coming up with an idea for a course project and what you're going to do, and stuff like that. Because as we get into the semester, you'll be doing homeworks and labs, and so I want you to, that way the course project will be behind you and you'll have some sort of ideas on what you're going to do. All right, I'm going to keep the chat open. If you have any questions throughout this lecture, let me know. Again, the slides will be put up on Canvas for tonight's lecture. So if you miss something, or the recording is going to be there too. And also just let me know if you can see this. Okay. Okay, so tonight I thought we would introduce data visualization, right? And how do we go from data to a visualization, right? You might think, well, that seems pretty obvious, but there are some rules to follow, and there's some good ways to go about doing this, and there's some not so good ways to go about doing this. And so we're going to initially start out with some of the good ways to do this and how to build a visualization. One way to understand this idea of visualizations is to kind of look at a visualization with it from its component parts, right? And see how these components are put together. Before we start that, I wanted to talk a little bit about this idea of a grammar or rules of grammar, right? And we're going to use this idea of grammar to help us put together some graphics, right? And so if you remember from elementary school where you learned how to put sentences together, right? A grammar is just a set of rules that tells you how to put clauses and phrases together, right? Tells you how to put sentences together. And if you approach graphics like this, or if you approach visualizations like this, it makes putting visualizations together a lot easier, right? And so we're going to think about not putting sentences together, but we're going to think about putting together graphics, right? Using this idea of a grammar of graphics. Right? So that being said, let's think about what goes into a grammar, right? And so it really kind of dictates how you put a sentence together. And really, when you use that sentence, right, you're communicating something to someone else in text, right? And so why they use a grammar of graphics, kind of the analogy here, is because is so you can kind of make that philosophical jump from language or text to a data visualization, which is in our case, in the case of this class, it's kind of a language of communication, right? Visualizations help you communicate something about your data, right? Or communicate something about model results, right? We're going to get into that eventually at some point in the semester where you run an analysis. And in that analysis, you want to visualize the results, right? And so we're going to think about building sentences, but we're going to think about building sentences in pictures. And those pictures are going to help us communicate something about our data. All right? Let's see if this works. Okay. So what does grammar offer? Why do we use something called grammar? Right? Well, when we get to later on the semester and we're putting together incredibly complicated graphics, it helps to know how those graphics are composed, what components compose those graphics, right? And so if you have some idea of the components of those graphics, that helps you understand complicated graphics a little bit easier, right? And so it gives us this kind of set of rules or a recipe to put graphics together, right? And it also gives us some sort of common foundation for understanding how many types of statistical graphics there are out there, okay? And so if you were to communicate, so let's say you build a graphic and you want to share it with somebody else and they want to alter it or edit it, right? If everybody's on the same page, if everybody is using the same sort of grammar, they can understand the components in that graphic and they can help change those components. So that's why we use this kind of idea of a grammar of graphics, right? It gives us this foundation of rules, and those rules are everybody kind of who works in the graphics world or works in the visualization world uses the same types of rules, right? And if you use the same type of rules, then you can edit other people's graphics, right? You know the components of their graphics. There are some things that a grammar cannot do, right? And we're going to talk about that as we go through the semester. We're going to talk about how do we do, there are things that grammar can't do. And so a couple things that grammar can't do is it can't really prescribe the best visualization for a task, right? That's pretty much up to you. Okay. And so what I'm going to say is if you have this task that you want to do, let's say we want to visualize this relationship between two variables, right? A grammar of graphics is going to tell you which visualization type to use. That's up to you. And you're going to learn that throughout this semester, right? Also, a grammar of graphics cannot really suggest the details of the way your visualization should appear, right? Or what it should look like. And so and so again, throughout the semester, you're going to learn what makes a good visualization and what makes a bad visualization, right? And also another thing, this is kind of tangential, but a grammar of graphics can't really support some sort of interaction, right? So how do you interact with graphics? We're not going to talk about it in this class, but there are packages out there, there are ways out there to make visualizations that are interactive, right? Okay. So we understand a graphic, right? We understand this grammar of graphics. The next thing I want to talk about a little bit is how do we actually get data, right? The data that you have in a spreadsheet or in a database and get it onto a visualization. What is that process, right? And so really what we're doing is we're taking data, right, and converting them in some systematic and logical way into the visual elements that make up the final graphic, right? So we're going to convert data into a visualization. Right? And the real important part or the real insight here is that all data visualization map to data values, right? They map data values. So everything on a visualization maps to some sort of data value. Okay. And so we're going to refer to these as features, these visual features that are mapped to data as aesthetics. Now, that when we get into coding, you'll see that the AES or aesthetics is a very important component of our ways to do visualizations, right? Or coding in R. So even though there are many different types of data visualizations, right? And really, on a first glance, if you were to look at a scatter plot or a pie,
We can't hear you, Professor.
how about now?
Yes.
Can you hear me now? Oh, okay. Sorry about that, everyone. Um, should I go back? I totally. Okay, so let me go back real quick.
When we lost you at scatter plots.
Oh, huh. Maybe something muted by mistake. Okay, thanks for that. So you could hear me in the beginning of this. You could be hearing me at the beginning of the lecture.
Yes.
Okay. Wow. I wonder why it muted all of a sudden. Okay. So let me repeat. So even though you have different types of visualizations, superficially they look incredibly different, but they're really there's a lot of commonalities, right? All different types of visualizations can be described with a common language, right? And that common language is that idea of aesthetics, right? So we can take this idea of aesthetics. The idea of aesthetics is taking data values and turning them into some sort of picture, right? Oh, that's it for that. Okay. Let's talk about aesthetics and types of data. All right. Okay. So all aesthetics fall into one of two groups, right? One that can represent continuous data, okay, and those that can't. And so continuous data values are, and again, the reason that I talk about this in very basic ways is because we're going to get complicated relatively quickly, right? And so what I want you to do is to think about these basic ideas. If you have a good idea of the basics, then the complicated stuff isn't that complicated, right? So again, all aesthetics fall into one of two groups: one data that can represent continuous data, and those can't, right? And you know what continuous data values are. So they're data values where the values are arbitrarily fine, and there's a lot of intermediates, right? In continuous data. Sorry. So position, shape, size, line width, all of the things in this figure can represent continuous data, right? But there are two things that only represent discrete data, right? And that's line width, I'm sorry, line type and shape. Okay, and so those two things, when we're thinking about categorical data, those two things are things that we're going to kind of have to when we think about categorical data, we'll be using shapes and line types. All the rest of the aesthetics here we can use with continuous and categorical data. All right. Oh, this didn't turn out so great. So this table, and I'll fix this before I upload this to Canvas, is kind of an idea of what are the types of quantitative variables that you have, right? And I gave you some examples. We're not going to go through all of this. I think most of you guys know this. Quantitative variables are the scales are continuous, right? And the description is, they're just arbitrary numerical values. Now we have quantitative numerical with discrete numbers, more like integers, right? And then we have qualitative, or we have categorical, right? Now, again, this table didn't work so great, so let's go to the next one. This table is a little bit more clear. I'll fix this before I put this up on Canvas. But we have qualitative or categorical data, right? And so an example of some sort of categorical data would be good, fair, poor, right? Where there's a discrete category for each one of these, right? Now, these could be ordered or unordered, right? So good, fair, poor has an order to it. However, if we were talking about political parties, Democrat, Republican, Libertarian, there really is no order there, Same with religion, right? If we were looking at religion as a category, you would say that there was really um, there's no order to those categories. And dealing with ordered categories versus non-ordered categories is a really important distinction. And we can think about that distinction when we build a visualization based on what type of variable we're using. And then the other two, date or time. Date and time is pretty important. They all have their idiosyncrasies. Dates could be continuous or discrete. Time could be continuous or discrete, depends on how you measure it or how you're analyzing it, how you're looking at it. And so how we deal with dates or times is in a visualization is very important. We'll get to that when we talk about looking at trends. But that's something that takes a little bit of special handling when we deal with dates and times. And then text is just text, right? And so just because there's free form text and we can think about free form text, we can also visualize that also. Okay. So scale and let's talk about, so we've talked about aesthetics, right? Now we need to talk about scales, right? And so and scales kind of really think about the types of aesthetics and where those aesthetics lay on the coordinate system, right? And so scales really map data values onto aesthetics. And in order to do that, we need to specify which data values correspond to which specific aesthetics values, right? And the mapping between data values and aesthetics, right, is created via this idea called scales. So what I want to do is I want to give you an example. Okay. And so, for example, if our graphic has an x-axis, and we need to specify which data values fall onto particular positions along this axis, we need to specify which data values are represented by what particular shapes or colors, right? So we need to specify which data values fall in a particular position and what colors they are or what shapes they are, right? And so we can do that here. Right? It's very simple. We can what positions. So where on the visualization or where on the figure are these aesthetics going to be placed? What shape they're going to be a part of, right? And what color we're going to use. These are all really important to think about. And you might think, oh, yeah, of course that's pretty obvious. But when we're putting a visualization together, it's really important to think about, well, where are these aesthetics going to lie? What shape am I going to use? Right? And what color am I going to use? So that's the idea of scale. So we have two main ideas that we've just kind of talked about so far. We've talked about aesthetics and we've talked about scales. So aesthetics is actually taking the data values and converting them to something visual. And a scale is where are we going to put those uh, objects? Are we going to color them or are we going to put them in different shapes? Okay. The next thing that we're going to add, this grammar, right? So we're thinking about this grammar of graphics. So we have aesthetics, we have scales, and now we're going to talk about coordinate systems, right? And so in order to make any sort of data visualization, you need to define what those scales are, right? So where are we going to put these different data values? Where are we going to put these different data values, right? And so for regular 2D visualizations, we have two numbers are required to uniquely specify where the point is, right? Remember in the old days in elementary school, we realized, we were taught that we needed two values to specify a point, right? And so the combination of the scale, right, and how they're arranged is called a coordinate system. Right? And so let me give you an example. So before we move on, and so for a two-dimensional plot, right, two scales are usually, but not necessarily, we have X and Y axis of the plot, right? So that's just your Y axis and your X axis, very basic right? But you also have to specify the relative arrangement of those scales, right? So conventionally, normally, the x-axis is horizontal, the y-axis is vertical, right? But you could choose other arrangements. There are other types of arrangements to put these coordinate systems in place, right? And so really, for an example, we could have the y-axis run at an angle relative to the x-axis. Or we could have one axis run in a circle and the other one run radially around within that circle, right? So even though conventionally the x is horizontal, the y is vertical, there are other options, right? So we're not relegated to that. There are certain instances where we use something where a conventional x and y axis is not appropriate. All right. So let's start with some easy stuff first. Let's start with our basic Cartesian coordinate figure, right? And this is the most widely used coordinate system for data visualization. Is that two-dimensional Cartesian coordinate system, right? Where each location is uniquely specified by an x and y point. Okay. And so these x and y axes run orthogonally to each other, which means they're placed at a right angle, right? And there's even spacing along the y-axis and the x-axis. Right? The two axes are continuous position scales, right? We talked a little bit about that in the last bunch of slides where we talked about scales, right? And these two position scales can represent both positive and negative real numbers, right? And so to fully specify this Cartesian coordinate system, we need to specify the range of numbers each axis covers, right? That's pretty easy to do. You guys have all seen this before, right? So here's our Cartesian coordinate system, right? With an x-axis with positive and negative numbers and a y-axis with positive and negative numbers, right? Remember, data values are not just numbers, right? There's some sort of units assigned to them. This is really, really important when we get to our labeling section of when we get to how we do labels, is we always have to make sure that we label our units, right? So for an example, your units could be temperature, right? Celsius or Fahrenheit. They could be distance in kilometers or miles, and time could be in minutes or hours. Always, always, always make sure to label your units, right? And the spacing between these grid lines, you can see these grid lines, the spacing between these grid lines along the axis corresponds to discrete steps in these data units, right? So each grid line is a discrete unit, a discrete step within these data units. What's really cool is a Cartesian coordinate system like this can have two axes that represent two different units, right? The one we saw before was similar units, right? Kind of anonymous. Here, we can use we can represent two different units, right? This situation kind of shows up when we mapping two different types of variables to x and y, right? So whenever the two axes are measured in different units, you can stress or compress one relative to the other, right? To maintain this kind of valid visualization of the data, right? And you can see here, I've done it three different ways, right? And so you might ask yourself, okay, which version of this is preferable, right? That might depend on the story you want to convey, right? It really depends on what you think is appropriate, right? And on the upper left, this type of tall, narrow figure, right, emphasizes a change along the y-axis. So if you really want to accentuate this y-axis change, then you would choose a visualization like that, right? And a short, wide figure like the one at the bottom emphasizes this change along the x-axis, right? If you really wanted to emphasize the x-axis, then you would show the bottom one, right? Ideally, what you want to choose is something that's sort of in the middle, right? Ensures that any important differences in position are noticeable. So this one in the upper right-hand corner kind of shows both of those. But all three of these can be correct, right? Neither one of these is incorrect. It really kind of depends on what you want to show. All right. If the X and Y axes are measured in the same units, then the grid spacings for the two axes should be equal, right? You may wonder what happens if you change the units of your data. Right? So if you notice here, if we wanted to change the units of the data, a change in units is kind of a linear transformation, right? It really depends on how you add the data or how you subtract a number from the data or multiply the data with another number, right? And so if you were to do that, you could say, okay, well, Cartesian coordinate systems are really they don't really care if you do such linear transformations, right? So we can transform our data and still get the same figure, right? And so let's look at these two figures. They're the same figure, but if you look closely, you can see that the values on the y-axis and the x-axis are different, right? Because the figure in part A is Fahrenheit, right? So this is the mapping of temperature in Houston versus temperature in San Diego. It's Fahrenheit. However, right, the one in the figure in the B figure, the one on the right, shows the same relationship, only measured in Celsius. Right? So we can see here that even though the grid lines are different, right, are in different location, and the numbers along the axes are different, the two visualizations look exactly the same. Why? Because it's the same. This is the same relationship. We've just changed the axes or the way we measure these variables. We can also have nonlinear axes, right? And so in a Cartesian system, the grid lines along the axis are spaced evenly, right? And in the resulting visualization, they're also spaced evenly, right? We're going to refer to this position scale, this scale, as linear, right? And so linear scales generally provide an accurate representation of the data, right? So there are scenarios but however, there are scenarios where nonlinear scales are preferred, right? Or nonlinear scales might work better with your data, right? In a nonlinear scale, the even spacing doesn't really correspond to the data units. The data units correspond to uneven spacing. And you're like, well, what does that mean? Let's take a look at this. Okay. The most common nonlinear scale, right, is the idea of a log scale. Okay? And you know that we do a lot of log transformations when we look at data. Right? And so the log scales are linear in multiplication, right? So for every unit step on the scale corresponds to multiplication with some sort of fixed value. Okay. And so to create a log scale, we're going to log transform the values. Right? So if you look at the top, the original data is just the data on a linear scale. All right. And then we log transform the data still on a linear scale. All right. Notice how the values are now at the same locations, right? However, the values are different, right? We've log transformed. And then we'll put the original data on a logarithmic scale, right? But really, we chose that because, and you think, well, 33.16 and 31.6 may seem like a strange choice, but I chose them because they were exactly halfway between 1 and 10, right? So when you look at this log scale, the original data on a logarithmic scale makes a lot more sense, okay? Because that's the original data on a logarithmic scale, right? One thing we have to think about too is really to make sure that we have the correct axis titles. Here, this is actually the base log because this is the original data on a logarithmic scale, so it's actually x, right? Not log 10x. Right? Let's talk a little bit more deeper about this, right? So mathematically, there's no difference between plotting a log transform data on a linear scale or plotting the data on a logarithmic scale, right? The only difference here lies in how you're going to label that individual axis. Right? And also, like I said, like the figure said, always, when plotting log transform data, always specify the base. You use base 10 or the natural log. Those are the two most common ones. Make sure you label the axes correctly. Right? In most cases, the labeling for a logarithmic scale is preferable, right? Because the one thing that you want to think about here is you want to allow the reader to interpret the numbers with as little mental burden as they can. Right? So you want to do things in a very straightforward way, a very easily understandable way, so your audience isn't confused by your figure. All right. And also, if you label them that way, there's also lesser a risk of confusion about the base of the algorithm, right? Is it a log 10 base or a natural log, right? We can get confused, right? Because when it comes to log transforming things, there are two different ways to do it, and that can be confusing if you don't use this all the time, right? So we can get confused about whether the data we're transforming using a natural log or log to the base 10. Right? It's not uncommon for labeling to be ambiguous, and we don't want that to happen either, right? So we don't want some sort of ambiguous labeling of our axes because we want it to be clear and understandable. It's not uncommon for labeling to be ambiguous, right? Log x, and if you do the log x, that really doesn't specify the base at all. It doesn't specify whether it's a natural log or log 10, right? Or base 10. So it's really important to be explicit and simple about your axis titles or labels, right? Because multiplication on a log scale looks like addition on a linear scale. Log scales are the natural choice for any data that have been obtained, whether you multiply or divide, right? So using a log scale is really the most appropriate way to do that, right? And also too, I have a student now who's calculating some odds ratios. In particular, if you're looking at odds ratios, if you have parameter estimates or model results and you're calculating odds ratios, they generally should be shown on a log scale. All right. Let's talk about um, this idea of scales, right? So we've taken a number of inhabitants in each county in Texas and divided it by the median number of inhabitants across the Texas counties, right? So total number of inhabitants in each county and divided it by the median number of inhabitants across all counties, right? And so the idea here is this resulting ratio. This is a ratio now, right? Population number divided by the mean, and Texas counties on the x-axis. And so notice that the resulting ratio is it is a number that can be smaller than one, right? And a ratio of actually 1 to 1 implies that the county has the same as the median number of inhabitants of all the counties, right? So when you visualize these ratios on a log scale, you can clearly see that the numbers in Texas are symmetrically distributed around the median. That makes sense because we divided by the median. So you have just as many counties above 1 to 1 as you do below 1 to 1. Okay. The most populous counties have over 100 times, right? If you look at Harris, Dallas, and Tarrant County, that's 100 times more than the counties that the least populous counties have, right? They have over 100 times fewer participants. I'm sorry, not participants, inhabitants, right? So when you look at these ratios, when you start to look at ratios and visualizing ratios, it's important to figure out, or it's important to remember what scale you're supposed to use, right? Now, let's do this on a linear scale instead of a log scale. Remember, I said before, whenever you're looking at ratios, you should do it on the log scale. let's see what it looks like on the linear scale, right? And so if you use the linear scale, it obscures these differences between a county with a median population number and a county with a much smaller population number than the median, right? Can you see that? So we have overemphasized ratios that are less than one, right? I'm sorry, that are greater than one, and we have all the ratios that are less than one, we can't really see, right? And so, like I said in 2 slides ago, this one, as a general rule, ratios should not be displayed on a linear scale. And you can see here that if you change the scales, it would make this makes for a really not very good visualization. Like I have it labeled here, bad, right? And so you see the differences here, right? And that's really important to think about. One thing that we're going to get into when you start building visualizations is you might start at this with this one and say, oh, well, that doesn't look so good. And so you might try something else, like on a log scale, right? You might say, oh, that looks better. That's a better way to visualize the differences or the relationships I'm trying to get at. So it's really important to kind of think about these things and build visualizations in an iterative fashion, right? The first visualization you come up with is never really the last one that you end up with, right? Okay. On a log scale, the value 1 is a natural midpoint, right? So it's very similar to the value 0 on a linear scale. For example, right, you can write 10 as 1 times 10 and 0.0 or 0.1 as 1 divided by 10, right? The value 0 can never really appear on a log scale, right? Because when you do a log scale, it lies infinitely far away from 1. Right? One way to see this is to consider that log of 0 is negative infinity. So you're never really going to see it, right? The alternative is to consider that you want to go from 1 to 0, right? And from that, what that does is it takes either an infinite number of divisions by a finite value, right? Or alternately, you can make one division by infinity. You might say, okay, that makes a little bit of sense, but it is kind of mathematically weird. I'll leave it with you to kind of think about that and think about when you looking at ratios or looking at anything on a log scale, it makes a lot more sense when you're using odds ratios or something that's been multiplied as opposed to a linear scale, right? Log scales are frequent. I mean, you think, okay, well, when am I ever going to use a log scale? Why is this important? Log scales are frequently used when data set contains numbers of very different magnitudes. Okay. You can see here for this Texas County data set, the one that had the most populous county had 4 million inhabitants in 2010, while the least populous had 82. Okay, so this is a huge range. When you have data that's a huge range like that, log scales are really, really helpful, right? So a log scale would be appropriate, right? Even if you hadn't divided the population numbers by their median and turned them into ratios. But then you think, okay, well, the log of 0 is negative infinity, right? So what would we do if there was a county with no inhabitants? Well, you couldn't, when you talk about log scale, you can't really show that on the log scale because it would lie at minus infinity. And of course, you can't plot minus infinity. So you have to think about that when you look at your values that you're trying to visualize. Does 0 included in there? What's the magnitude of your values, right? And so you visualize it on the log scale or not? In this situation, right? Let's say you do have a 0, right? You do have a 0, so you can't really use the log scale. Can't really log transform a data set with a 0 in it. Right? So in this situation, the recommendation is sometimes to use the square root scale. Okay, so the square root scale is a little bit different, but the same, right? Just like the log scale, the square root scale compresses larger numbers into a smaller range. That's basically what the log scale does too. It takes these huge magnitude values and kind of squishes them all together, right? However, a square root scale allows you for a presence of 0 because you can take the square root of 0. Square root of 0 is 0, whereas the log of 0 is negative infinity, right? There really are kind of two problems with the square root scale. One, the linear scale with one step, on a linear scale, one unit step corresponds to addition or subtraction of a constant value, right? On a log scale, it corresponds to a multiplication or division by a constant value. There's no really rule for a square root scale. Remember, a square root is not multiplication or division, it's not addition or subtraction. So that's kind of something to think about, right? And the meaning of a unit step on a square root scale depends on the scale value at which you are starting. So it depends on where you're starting from, your starting point. You could be starting from a negative number, or you could start from a really large positive number, right? And secondly, it's really unclear how to best place your ticks, those little lines that align with the number. That's an axis tick, right? So on a square root scale, it's unclear where to put them. Where should we put them, right? If you want to put in even space ticks, right, you would have to place them at the squares, right? 2, 4, and 6, right? But at axis tick, for example, position 0, 4, 25, 49, 81, right, wouldn't really make sense. That's every second scale. I'm sorry, every second square. That doesn't really make sense either. Alternatively, you could put them at all the linear intervals, 10, 20, 30. But then again, now you have too few ticks. You have too many ticks at the bottom near 0, and you have too few ticks at the top. All right. So we've placed axis ticks, and if you look at the bottom, right, where we have the original data, we placed axis ticks as 1, 5, 10, 20, 30, 40, 50. And you can see that the distances between those change, right? You can see the distance between 0 and 1 is different from the distance between 40 and 50. Okay. But they do provide a reasonable covering of the data that we have. So again, you might think, well, that doesn't, I mean, plotting a square root transform data can't be that hard. But when you think about the intricacies of doing this, there are a lot of things to consider. And despite some of the things that we've talked about, these kind of issues that we have to deal with square root scales, they are valid position scales, right? And they have appropriate applications, right? Just like the log scale is a natural scale for ratios, one could argue that the square root scale is a natural scale for data that comes in squares. Straightforward. And so let's think about an idea where data comes in squares. Right. So one scenario in which the data are naturally squares are in the context of some sort of region, some sort of geographic region. In this case, we're going to use states. If we show area, right? Remember area, the area's got the square in it, right? It's a square mile. So if we're showing the geographic area, we're highlighting the region's linear extent from east to west or north to south. Right? And these extents could be relevant, for example, if we're wondering how long it might take to drive across a region. How long might it take to drive across New York versus Pennsylvania? All right. And these are all a function of this area, right? So even though these states are quite different, the time it will take to drive across each state will more closely resemble the figure on the right, right? Because that's area in square miles, right? On the square root scale. The figure on the left is on a linear scale, right? Notice, I mean, you can see that on the linear scale on A, all of the values are the equidistant apart. 1,000 or 10,000 is equidistant apart from 20,000. But on the B figure, now they're on the square scale, right? They're on the square root scale. So 40,000 and 50,000 are closer together, right? And so the time it's going to take to drive across each state makes more sense for figure B, because that's on the square root scale, because that's how we've measured the area, right? It's square miles. All right. Coordinates with curved axes. You're like, well, wait a second. We've gone from straight to logarithmic, changing the scales. Now we're going to go with axes that are curved, right? And so the stuff we've talked about already has two straight axes, right, at right angles to orthogonal to themselves. There are other there are other coordinate systems, right? And we can deal with those other coordinate systems, and some of them are curved, right? And in particular, there's this idea of a polar coordinate system, right? And in a polar coordinate system, we look at the values, and those value positions are based on an angle and a radial distance from the origin, right? So that angle axis is actually circular. So what we can do here is we can take the figure on the right, I'm sorry, the figure on the left, and turn it into a polar coordinate system on the right. Okay. Polar coordinates, and you might think to yourself, well, I'm never going to use a polar coordinate system. They can be useful. So these polar coordinate plots can be incredibly useful for data that has some sort of periodicity to it, right? Kind of has a periodic nature to it, such that the data values at one end of the scale can be logically joined to the data values at the other, right? Kind of year or season, right? Because there's a period to those values, right? I'll give you an example, right? Consider the days in the year. So December 31st is the last day of the year, but it's also the day before the first day of the year. Okay? And so if we want to show how some quantity varies over a year, it might be more appropriate to use a polar coordinate plot with the angle coordinate specifying each day. Right? Let's look at an example here. This is an example of temperature. So temperature normals, right, are average temperatures that aren't tied to any specific year, right? And December 31st can be just thought as 360 days, 66 days later than January 1st, right? Because temperature normals include the 20th of February, right? And also one day earlier. So you can see and I think this is a really good example of by plotting these normal temperatures in a polar coordinate system, you can emphasize this idea of a cyclical process, right? So temperature really works cyclically. Okay? And so if you were to plot this in a Cartesian coordinate system, that kind of idea of period of this cyclical property is obscured, right? Because temperature values in late December and early January are shown on opposite sides of a Cartesian coordinate figure, right? And they don't form like this kind of idea of a single visual unit. Here, this emphasizes that idea of this cyclical property of temperatures. December 31st is also connected to January 1st, right? And so you can kind of go around here and it gives you a better idea. And not all data has a cyclical property to it, but we can use a polar coordinate plot to look at data that has some sort of cyclical identity to it. The last thing I want to talk about is the other setting where we encounter this idea of curved axis is in the context of geospatial data, right? We're gonna spend a whole lecture on how to visualize geospatial data, right? And so, but you have to remember that really locations, on a map are specified by longitude and latitude. I'm sorry, longitude and latitude. However, we all know that the Earth is a sphere, right? So drawing longitude and latitude like we did in the upper left here is misleading, right? And kind of not really recommended. Instead, we can use various types of a projection that attempt to kind of minimize this uh, kind of distortion of taking a curved surface and putting it on a flat surface, right? And so we can strike a sort of a different balance between conserving areas or angles that are relative to true shape lines on a globe, right? So you can see that the way we choose a projection really accentuates different parts of the globe. And some make more sense, and some don't make that much sense. And so when we get to mapping spatial data, when we get to visualizing spatial data, we'll go through this idea of projections and how to deal with projections. All right, any questions so far? Okay. The last thing I want to talk about. So what have we talked about so far? We've talked about aesthetics. We've talked about scales. Okay? And we've talked about coordinate systems or axes, coordinate systems. The last thing I want to talk about is colors, color scales. Now, when we talk about color scales, I mean, there's a whole world of research out there that talks about colors and how we deal with colors, right? And so we're going to leverage colors when we build visualizations, right? There are three fundamental uses for color. We can use color to distinguish groups, we can use color to represent data values, and we can use color to highlight parts of the visualization that we think are important. All right. Now there's this package where we can frequently use colors as a means to distinguish discrete items that don't have any order. All right. In that case, we're going to use a qualitative color scale. Okay. There's no order here. However, every color is discrete. Right. That's what I mean by discrete scales. So these scales are finite. So it's not infinite number of colors, and they're chosen to look very distinct from each other, right? The second condition requires that no color should stand out relative to the others. If you look at all these colors, they all look relatively, not one jumps out at you. Okay. That means it's all discrete categories. However, they're all relatively benign, right? We're not using anything, we're not using these color scales to highlight anything, right? And these colors should not create any impression of an order. There are color scales out there. We'll talk about it in a second, where we're going to use colors to create an impression of order. Right? There's lots of color scales, appropriate color scales that are available for this type of idea, this type of qualitative scale idea. All right. In this example, we're going to look at population growth from 2000 to 2010, and this is an example of a qualitative color scale. This is percent population growth for each state in the United States. The coloring kind of says what states have in the same region have experienced similar population growth. Right? So it kind of looks at these idea of regions and which ones have had similar population growth. Right? In particular, let's kind of dive into this a little bit. In particular, states in the West and the South have seen the largest population increases, where the Midwest and the Northeast are more yellow, right? Remember, there's no order to this. We're just kind of trying to identify these regions, right? So what we're interested in, if I was putting this figure together, what I want to do is I'd be interested in what regions show the highest amount of growth, right? And you can see that the West in this plot shows the highest amount of growth because the bars are at the top, right? And the ones that are yellow show the Northeast region is showing much slower growth. Does that make sense? This is a really good example of how we, excuse me, it's a really good example of how we use these qualitative color scales to look at categories, but not highlight anything. We have another color scale for that. Like I said, we can also use color to represent data values, right? They can use data values such as income, temperature, or speed, right? And in this case, we're going to use a sequential scale, right? Because numbers increase or decrease. So we can use colors that increase or decrease, but it's kind of same shade, right? And so this kind of color scale shows what values are larger or smaller than the other, or how far apart values are from each other, right? And so the second point that I bring up here is that implies that this color scale needs to be perceived at a uniform across its range, right? So numbers 1, 2, 3, 4, 5 are uniform. So we're looking at colors like that. The colors have to be uniform, just like the numbers, just like the values, right? And so this is kind of an idea of a uniform gradient, as it were, right? So or a sequence. And you can see that as in blues, as the values increase, the color gets darker, right? These sequential scales can be based on a single hue, right? So to go from light blue to dark blue, they can multi-hue scales or from like dark red to light yellow, or you can have a scale that's got many hues in it, right? So and these kind of hues can be seen like in the natural world, right? If you're going from dark red, green, blue, or light yellow, or dark purple to light green, right? Um, and the third, and then we could the reverse, if you go to dark yellow to light blue, doesn't really look that, it looks kind of unnatural. It doesn't make good use of a sequential scale. So when we think about a sequential scale, make sure that you kind of have an idea of, what looks good and what you're trying to portray. And that'll help you identify what scale to use, right? Now again, there's a package in R called R Color Brewer that has all of these selections in it, and you can choose whatever color you like, right? Like this. So let's look at this. And this is the annual median income in Texas, right? And so really we can use this we can use this to represent some data values, right? As colors, if we want to show how data values vary across geographic regions, right? And so in this map, we drew a map of geographic regions and colored them by data values, right? So lighter values are less, darker values are more, right? And so this is a really great way to kind of say, okay, where are the counties? I think this is counties. Counties have the highest median income. And see that adding a sequential color really allows the reader to identify what's going on in this map really, really quickly. And so sequential colors can be very, very powerful, really a great addition. In some cases, we kind of have to look at the deviation of the data values in two directions, right? So we have a midpoint and we want to go to either direction. And one example of this is that if you have a data set that has positive and negative values and you've centered on 0, right? And so the color scale in this case we call diverging. And so they start at 0 or start at some middle point and they diverge in two different directions, right? And so the one thing that we have to be considerate of here is that each of the directions is the same, right? And it needs to be balanced, right? So the progression from light to dark on the outside is approximately the same in either direction, because that's what you're trying to portray here, right? Otherwise, if you didn't do that, the magnitude of the data value would depend on whether it fell above or below the midpoint line. You really have to choose that midpoint explicitly, right? Wherever the midpoint of your data is, and then an equal amount at the lower end and an equal amount at the upper end. So here we have a map of people people identifying as white in Texas counties, right? So even though the percentage is a positive number, even though percents are a positive number, we can use a diverging scale here because 50%, we can use 50% as a diverging midpoint value. Right? It's kind of anything less than 50%, anything more than 50%. Okay. So this visualization really clearly shows that where whites are in the majority and where they are in the minority, right? And it also shows where whites and non-whites occur in approximately equal proportions, right? So it looks like the percentage of people identifying as white is greater in the Southwest, and the people that are identifying as white is, I'm sorry, people identifying as percent as people identifying as white is less in the Southwest and greater in the Northeast. And then you know where the 50% line is, so you can kind of identify what counties it's 50-50. And so, like I said before, even even though we kind of use it for positive and negative values, it doesn't necessarily is restricted to that. If you have a data set where you have a midpoint that makes sense, you can use that. It doesn't have to be negative or positive, right? The last thing or the other thing we can use color is to highlight something that we want the audience to really focus on, right? And color can be a really great way to do that, right? There may be specific categories you want to highlight. There might be points or areas that you want to highlight. And so this effect, if you want to highlight something, there's nothing wrong with highlighting something. This effect can be achieved with a color scale with an accent, right? And so what that what that has is what that encompasses is or is a part of is you have a color set, and then within that color set you have it's mainly like very subtle hues, and then you have a couple categories that really stand out, right? In this case, right? So you can see on the left hand side, most of these hues are very subtle, and then you have two or three colors, or you have three colors that really stand out that can really accent these things, right? So each of these examples has four kind of base colors and three accent colors. And those accent colors, we can derive those accent colors in a few different ways, right? So we can take the existing color and lighten it or desaturate it while darkening others. We can take grayish values, right? So the second one, but bunch of really gray values, and then pair them with really bright colors. And then the third way is we can just take an existing accent color scale, right? And we can just use the existing accent color scale. And just really accentuate those three colors on the right for that bottom example. So let's look at this data again, right? We'll see that our use of color here changes, right? And so here's an example of the same data. We can support differing stories with different coloring approaches. Here we're going to highlight two specific states, right? Texas and Louisiana. Excuse me. Both states are in the South. They're right next to each other, right? Yet Texas was the fifth fastest growing state within the US, whereas Louisiana was the third slowest growing state. So when we look at that, we can say, okay, well, if that's the story we want to tell a story that says, even if you're in the South and the states are right next to each other, the population growth can be wildly different. Okay? So that just by choosing a different color scale, we can tell a different story, right? So it really depends on the story you're trying to tell with the visualization that you have. Right? So think about that when you're choosing colors. What's the story I'm trying to tell? What am I trying to communicate to my audience? Right? And last but not least, when working with accent colors, right, it's really important that the baseline color doesn't compete for attention, right? In this case, notice how drab the baseline colors are, right? They're really drab. And yet they work well to support the accent color, right? It's easy to make the mistake of using baseline colors that are too colorful, right? And then so they end up competing for the reader's attention against the accent colors. Make sure your baseline colors are really benign, right? Or one of the easy ways to do this is just remove all color from the elements except for the highlighted data categories, right? So in this case, we could just remove the gray and just keep the red. If you're confused, if you think, well, does it really show? Is it taken away? You can do something like that. All right, so that's color. So let's kind of wrap up. Let's kind of sum up what we've talked about so far. Right? And what we've talked about is we talked about a grammar of graphics, so how we take these components and put them together. We remember the components from the beginning of lecture. We talked about aesthetics, and how we take those data values and put them, how we visualize those data values, right? We've talked about scales, so the x-axis and the y-axis, how we measure, how we visualize those scales, right? And then we've added coordinate systems. So what kind of different coordinate systems are we going to use? And then the last thing we talked about was colors. So we have four components that we talked about, four components that make up this idea of grammar of graphics, right? So it's kind of like a subject, noun, the verb, and that sort of stuff that you learned when you were putting together sentences in elementary school. So if you think about those four components, right, and those four components are pretty common throughout every single visualization. If you have each four of those components and you have manipulated those four components, or that you've put those four components together, then you have a graphic, right? And that's one thing you can always think about. You can always go back to the grammar of graphics and say, okay, I've got, I have my axes, I have my I'm sorry, I have my scales, I have my aesthetics, I have my colors, I have my coordinate system, and I've got everything. I've got my visualization, right? And when I put that visualization together, then I can tweak or change, because you have options and different varieties for each one of those four components. You can change that to change your visualization. Okay. I think we're gonna stop there. So that's from data to visualization. We just put together from data to visualization. We really only have 15 minutes left, so I don't think I think we're gonna call it there. We're not gonna go into any I won't work on next week's lecture or last week's lecture. I think what I'll do is we'll just go over that first thing next week, so you guys can get some coding experience, or at least some background to code, so you can start doing your homeworks. Any questions so far on what we talked about tonight, what we talked about last week? Okay, well, that's all I have for this evening. Again,